This is the PHET, Physics Educational Technology Circuit Construction Kit. And I took as many resistors as I possibly could and put them in this ladder or infinite resistance circuit. Okay, it's not infinite. And then I put a battery in here. And if when I show the current here, we can see that the current is going through here. Here, of course, it has to split up. So it's less current over here, less and less current, and very little towards the end. I actually don't need to show the current for my purposes, but what I want to show are the values. So I used identical resistors. That's a hallmark of, or important hallmark of this particular circuit. Identical resistors that are arranged in series and then in parallel, and again in series and in parallel, and then again in series, and so on. I chose a battery voltage of 89 volts. Seems like an weird number to use, but we can identify it already as a Fibonacci number, and that'll become important in the analysis because it just makes it easy. All right, let's measure values, which are voltages. By the way, don't pay attention to negatives right here. So we're just going to say, hey, we got 1 volt. So 1 and 1 and 2 and 3. And we can see the first Fibonacci numbers. 5 and up. Didn't mean to do that. 8 and 13. 21. 34. And did it again. 55. There we go. And of course, the last one here on the battery itself is 89. So a nice Fibonacci sequence. Let's look at the currents. Here, 0.1 amps. I'm just going to call it 1. So let's assume that we had a 1 ohm resistors all the way through, okay? So 1 amp, another 1, 2, 3, 5. I notice that my current meter is a little bit at the bottom here. 8, 1, 13, 21, 34, and 55. So again, nice Fibonacci sequence. Of course, that's not a surprise, or shouldn't be a surprise, that both the current and the voltage show Fibonacci. If one shows, then the other one must show, because that would be by Ohm's law, which I just clicked on. So here's Ohm's law. If the voltage has certain Fibonacci sequence, then the current right here, intensity of current, also has the same. All right, next, let's look at the resistance. All right. So when we look at the resistance, we would have these two in series here. So 10 plus 10 is 20. And then we have it in parallel to this one here. So it would be the reciprocals, which is according to the rules for series and parallel circuits. So we would have 1 over 20 plus 1 over 10, which is 3 over 20. And then invert that again, so 20 over 3. Okay, it doesn't sound Fibonacci now, so I'm going to do a little bit different in Excel in just a moment. But first of all, I want to show that when we go to a series circuit, this is the formula that I was just using. Simply add the resistors, and in each series circuit, I only had, or part of the series circuit, I only had 2 resistors, so 10 plus 10 in my case. But when I do that, put them in parallel, then of course I need to follow this formula here. So that's why I said 1 over 10 plus 1 over 20, and then I came up with 3 over 20, which again I had to invert, and I came up with 20 over 3. So again, because of these numbers here, the 10 just being a little bit too cumbersome now as I'm adding the resistors, I'm going to change them back to 1, and I'm going to use an Excel sheet. So here it is. And I have my first 2 resistors are 1. Again, I changed from 10 to 1. So 1 plus 1 equals to 2 right here. Here's the formula in Excel. Simply add the 2. That's it. And then for parallel, as I said, here's the formula. 1 divided by 2 plus 1 divided by 1. And then invert again with the 1 over here in the front. And I come up with a fraction of 2/3. then the next resistor is going to be in series with that. So simply add 1 ohm plus 2/3, which is 5/3. And then the 5/3 right here is in parallel with the next 1 ohm. So again, it's going to be 1 over 5/3 plus 1 over 1, invert again, and come up with 5/8, and so on. And when we look at these interim results between the resistances, then we can see a nice Fibonacci sequence, 2, 3, 5, 8, 13, 21, 34, and so on. And down here for the parallel one as well. Of course, the two are linked because they're one and the same circuit. So these are only the interim results. So here we would have the 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, all as nice fractions. And when we're all done with it, the 89 over 55, for example, at the end, that would be the equivalent resistance. If I plug that into 89 over 55 into a calculator, there it is, 1.618 and so on. And I compare it to the golden ratio, which is the end product of the end result of the Fibonacci sequence, 1.618, just the same as it should be. And that is the Fibonacci sequence for this ladder or infinite resistance chain.